Hi, everybody. In this lecture, we're going to be talking about not just Earth's oceans, but all of its water. But we've titled it Oceans here, so let's take a look. Time to begin. So, water on Earth. What on Earth? No, not what on Earth, water on Earth. The most abundant chemical compound that is near the Earth's surface is dihydrogen monoxide. It covers about 70 to 75% of the Earth's surface. Between 97% to 98% or so is part of the ocean, meaning that it is salt water. Only about 2 to 3% is fresh water, and of that fresh water, most of it is tied up in our Earth in the ice caps. And so that's not really usable. So less than a third of the fresh water that's available on Earth is actually not really available for use. The hydrologic cycle, actually the water cycle, we've talked about in a previous lecture when we were talking about the cycling of matter in an ecosystem. So if you want an update on that, go back to the ecology lecture and take a look at that. But just real quick, the hydrologic cycle is essentially evaporation of water from the oceans along with other sources of water. The water vapor is then transported to other locations. It condenses and precipitates to where it precipitates back to Earth as rain or snow or sleet or hail. So the water then returns to the Earth. So if we take a look at a diagram here, a pie chart of all of Earth's water, we see that about 97-98% of Earth's water is ocean water, that is salty. Only roughly 2 to 3% is fresh water. And of that 2 to 3%, most of it is locked up in ice. And then we have some that is in sediments and groundwater, and then we have rivers, lakes, and streams, which makes up about 0.8%. And then there's water vapor in the atmosphere, which is 0.004%. So that gives you a breakdown of water on Earth, where we find it and everything. So here's the hydrologic cycle. Okay, so water on Earth, wherever that water is, evaporates. We get clouds. What we see is actually clouds, is actually condensed water particles. It's not exactly water vapor. If it were just water vapor, we wouldn't see it. So it evaporates. We get clouds. Clouds then get denser and denser, and then they precipitate over land, and so you end up with fresh water on the land. So when water evaporates out of the ocean, the salt doesn't go with it, so that's where we get fresh water. So fresh water comes to Earth by way of precipitation. This is our basic freshwater source. 2/3 returns to the Earth's atmosphere. About a third of it ends up roding downhill and joining other water sources, streams and rivers and whatnot like that as runoff. And so you end up with groundwater being absorbed by the surface, runoff from the ground, which also then will work towards, and if we think back to a previous lecture on erosion, weathering and erosion, all of this water runoff coming down the mountains aids in that weathering and erosion. So runoff and groundwater distribution depends on the soil, the types, the dryness, and the amount of vegetation, the steepness of the slopes, and the rate of the rainfall. So this water is coming down mountains and hills and whatnot like that, and it's going to be carrying materials with it. And here we have a diagram of water moving through the valleys by way of a stream, and it's going to be running off down both sides, joining the stream, and eventually some of that is going to go back into groundwater. The river could end up going into the ocean, so it blends with the salt water and you have an estuary. And at any point in time, you're going to have evaporation, condensation, and precipitation again. Earth's surface water. Collectively, all of the water that's in streams, ponds, lakes, reservoirs, this all is referred to as surface water. And we have areas that are referred to as watersheds, and that's because as the all of the water in a particular area during the precipitation part of the hydrologic cycle, all of that water in particular watersheds will come together into particular bodies of water that are usually running. So any land area that's drained by a particular stream or streams or rivers, this is referred to as a watershed. So, for instance, in a particular area, all of the water, the runoff that comes into a particular area will go into one particular stream, and that where it comes together, all of that area is referred to as the same watershed. So two adjacent watersheds separated by a divide, you'll end up with water going in the opposite directions. The continental divide separates watersheds draining into opposite sides of the continent. And you can also have, if you have two river basins, and you'll have water moving into two river basins, and it all depends on the direction of the water flow. So here are some areas that are watersheds. The Mississippi River, which is one of the, I guess, the mighty Mississippi, really drains most of the central United States. The Colorado River drains the area running through the mountains of the Colorados. Columbia River watershed is in the Pacific Northwest. And so you have these different watersheds where these large rivers then flow into the ocean. Here are the river basins, or Georgia's river basins, which are the watersheds here in Georgia. The Flint, you have the Flint, where all of this is going to drain into the Flint River. We have the Savannah River Basin. All of that's going to drain into the Savannah River, etc. So you can see the areas of Georgia that will drain into these particular river basins. So these are our watersheds. Groundwater is that water that's underground. So a lot of places in South Georgia have areas that are actually that are surface wells are very close to the surface, and so artesian wells, and so you can easily get groundwater to come up. But groundwater is underground water. Typically, it could be between rock layers. It could be just in the soil. So underground water saturating open spaces between rock and soil particles. So it could be within the soil. It could actually be between rock layers and trapped there, and so it has to come out. So it percolates downward from the surface. This actually cleans the water a great deal. Groundwater, we have a supply of groundwater that's 25 times larger than the supply of surface freshwater. And this groundwater could be as much as 100 meters, but usually it's less than 100 meters from the surface of the ground. So freshwater as a resource. Obviously, freshwater is required for life. And also modern industry. And in previous lectures, we've talked about why water is required for life. Water is required for life not just because it prevents us from being thirsty, but because why? Do you remember? Because all of the chemistry of life takes place in an aqueous solution. This is why living things need water. The average U.S. usage is about 5,700 liters per day. About 40% of that is agriculture, 40% for electricity, 10% industrial, and 10% domestic. Most of this comes from surface water. More sediments, bacteria, and pollutants are in the surface. This means it requires filtration and whatnot, and surface water does depend on precipitation. Most groundwater doesn't. So about 40% comes from groundwater because of the fact that it's percolated through lots of layers of soil and whatnot like that. It's relatively free of bacteria and suspended particles, but it does often have dissolved minerals in it, and it could very well be more expensive to get because you do have to pump it up to the surface. Seawater. This is the salty part of our water, and the 70% is covered with seawater. Average depth of about 3,800 meters. Only about 30% of the Earth's land is Earth is dry land. Um, Most of our ocean is still unexplored. We know more about the surface of the moon than we know about the bottom of the ocean. It's much easier to get to survive on the moon than it would be at the bottom of the ocean. Going from Earth into space, you only have a difference of about 15 pounds per square inch of pressure. But for every 33 feet of seawater that you go down, you're going to add yet another atmosphere of pressure. So at 33 feet, you're already at 2 atmospheres of pressure, 1 atmosphere of water, 1 atmosphere of air. 33 feet, that's not a lot. That means by the time that you get to essentially 100 feet, you have 3 atmospheres of water and 1 atmosphere of air above your head. So you're at the pressure equal to 4 times the pressure that you're at the surface at 100 feet. So think about as you continue to go down. So that's why we know more about the surface of the moon than we do about the bottoms of the ocean. So our oceans and seas. We call them the 7 seas, even though the ocean is really one continuous body of salt water that covers the Earth's surface. The principal regions, we have the Atlantic Ocean, the Pacific Ocean, and the Indian Ocean. Now, each of those oceans have areas within them that have other names, but primarily these are the big names here: the Atlantic, the Pacific, and the Indian Ocean. A sea is a smaller region that is distinguished by particular characteristics, something like the Mediterranean Sea, the Gulf of Mexico, the Caribbean Sea. These are all bounded by land in some way, islands or peninsulas, that sort of thing. So we can see here. We can see here on this particular diagram all of the Earth's oceans are how all of the Earth's oceans are connected. So the nature of seawater, the salinity. Let's think about. I mean, the first thing that we think about when we think about ocean water is the saline factor. Well, what exactly is it? It's mostly sodium chloride, but you also have other chlorides: magnesium chloride, calcium chloride. There are other chlorides that are there. And so you do have the salt dissolved per kilogram of seawater. So it's about 35%. 35% is the typical percentage of salt in seawater by mass. It doesn't really change with the changes in the water temperature, although in various places, as the water evaporates, then you're going to get more salinity. As water evaporates, you get more salinity because the salt doesn't evaporate, and so you get a greater salinity, and so it does sink. Concentration is increased by evaporation and ice formation, so you get saltier down deep, especially up in the Arctic and in the Antarctic. But this decreases when we have precipitation, which makes sense because when it rains a great deal in a particular area, that's going to dilute the salt water.